Welcome to the second part of this lecture series on functional programming in F#. In the previous lecture we talked a bit about programming generally and programming languages and why it is important that we expand our horizons, expand our minds and learn multiple programming paradigms and multiple programming languages. In this lecture we will be starting to scratch the surface of functional programming, but before we do so, I think it's useful to put this into some kind of historical context of where does this fit in this grander scheme of things in this field of computer languages and computer science. So if we go back, programming starts way back with Babbage and mechanical computers. We don't need to go that far back, but really modern computers start basically in the 30s with Alan Turing. We're starting to work on a mathematical problem really, which is the Entscheidungsproblem, the decidability problem from Hilbert. Where they ask the question, can we decide whether an algorithm will give a universal answer, yes or no, or another way to formulate this, is this problem computable? Like, can we guarantee that this computation will finish in an infinite time? And this was something that mathematicians were interested in and Turing started working on. And his method of doing this was by inventing the very famous Turing machine, which is really a mathematical invention, but if we can turn it into basically a very simple thing. It's a BIOS, it's memory, and there are registers. And the BIOS contains some initial little set of instructions how to load the programs, and then you can load the program from memory, which is a paper strip that can be read and written and rewritten, and this is important. So the Turing machine is a finite state machine, and it will provide a computational answer to a problem by changing its state over and over and over again according to a computational recipe, which is our algorithm, and then it provides an answer. And this is all fine. At the same time with Turing, there was a guy in America, a logician. His name was Alonzo Church, and he was also interested in the same problem, but he had a completely different approach. He invented something that he called lambda calculus, where he used only simple functions to do computations and to express things. And it turned out that the Church's lambda calculus was actually completely equivalent or isomorphic to first order logic, almost at least. So he invented a new system of logic based on pure mathematical simple functions, which was very powerful. And then if you are an engineer and you need to invent a mechanical computer or electrical computer, then it turns out that Church's ideas weren't really easy to implement in hardware in any way, form or way. But Turing's ideas were pretty simple for binary computers. And the Second World War started. They started building computers to crack the Enigma codes, and of course everything was based on Turing's ideas, and he was central in developing these ideas. This meant that the first programmers and the first computers, they were all based on the Turing state machine idea, and everybody programmed the machines as the machines they were. That was the level of abstraction. They didn't have any resources early on, so they couldn't really do anything more advanced. So things were programmed with cables and switches. But already in 1952, John McCarthy invented a programming language called Lisp, which was based on the lambda function as the central idea. But unfortunately for John McCarthy back then, Lisp couldn't be really used for anything seriously useful, because the computers were so small and so primitive that you would use up most of the resources of computers just to run Lisp. So the first generation of programmers, they were all of the Turing von Neumann school in state machine programming. And this went on for quite many years. Computers were tiny, they had very little memory, and they were hard to program. So the school of programmers that came out of this, they were all thinking like computers, mapping their heads and their ideas onto the way the computer functioned. And this gave rise to, then later, to programming languages, normal imperative programming languages that we use today, like C and Fortran and Java and so on. And Church's ideas, they were more of an academic interest. Now, long gone are the times where computers are so tiny that we can't afford to use the ideas from Church. And we should really have a little look at what are the virtues of his ideas and compare them to Turing's ideas. And really, if you think about the state machine, it's what we call an imperative idea. And the languages are based on statements, where a statement is what to do next. So it's basically a series and then. Whereas if you look at the lambda calculus and you look at those ideas, it's really declarative and based on mathematical expressions, where an expression is a complete whole set of instructions of what you want. And it's more what than how. So somebody had a nice analogy that when an imperative programmer goes to a bar and orders a coffee, he goes up to the bar and he tells the barista how he should heat his water, how he should warm his milk, how he should grind the coffee, how he should fill the coffee maker, how he should do all these things and what buttons to press, and then finally he will be presented with a cappuccino. Whereas the Churchian programmer comes in and he says, give me a large cappuccino with a little bit of cinnamon on top. And of course, both will get what they want. One is much more detailed, gives the guy or girl who orders much more control over what they get, but it's also a lot more tedious. Whereas the functional programmer or the Churchian programmer, he will just say what he wants and he will get it. And this is really at the heart of this, because it's a lot less complex to just state what you want rather than describe the detailed recipe of how you want it. And back in the day, people were programming tiny small little programs, and it wasn't really a big issue how you programmed them, because you didn't have memory and capacity to do a lot. But these days, programs, when you take in all the libraries, everything that you use, easily end up being 1 million lines of code, and the complexity is staggering. And complexity is a problem, because we do get loads of unintentional effects out of our programs. We call them bugs usually. And we get long codes, and they are hard to extend. So that's at the heart of why we should maybe look at this alternative way of doing things. So functional programming is based on pure mathematical functions. I will talk much more at length about pure mathematical functions, but a pure mathematical function is a simple little thing. It's a black box. It contains all it needs to know about the world. It will take a single input and it will produce a single output. And inside of it, there is no state. There are no variables. It cannot talk to the network. It cannot read the disk. It cannot access global variables. It has access to none of the sort. Yes?
So this is a lambda function or a mathematical function?
This is just a mathematical function.
But how about mathematical functions taking several input parameters?
That will be for another lecture. So that's a very good question, but this input here and this output here need not be a simple number. They can be immensely complicated data structures. So that's basically the answer. But there are other interesting features and how to deal with multivariate functions that we'll look at later. So these functions are the big virtue with these things is that these are mathematically well defined. They have, in principle, we can say that all of the mathematics of functions will apply, which is a great help when we're trying to do things and make things stable and help us not fall off the ship. By using these, you will automatically favor declarative expressions over statements. They give us what functional programmers like to call equational reasoning, so we can actually use the rules of mathematics to think about our code. And this does not mean that we are going to be mathematicians and sit and do heavy equations and stuff, but it gives us certain properties that are going to make our life a lot easier, actually, once you get used to it. So we build all of this programming theory on a solid mathematical foundation, really. It then turns out that Church's first attempt at lambda calculus was a little bit too good. It was a little bit too powerful and needed to be restricted a bit, because you could actually express paradoxes in it, and that wasn't good, not from a mathematician's point of view. So he came up with something that is now known as type theory to sort of restrict when and how you could apply your lambda calculus. And this turns out to be super useful for computer programmers because it allows us to put some rules on how we can use our code in what situations, and again help us abstract and structure our codes in a good way and not misuse them. And this is also something we will look at later. Because all we in the end really want is to be able to have as many guarantees as possible about the program behavior that we have, that it will behave correctly. That in another way, we don't really like bugs. And said slightly sort of on the edge is that mathematicians have spent the past 2,000, 3,000 years perfecting their language and perfecting their techniques in order to be able to express themselves with absolute clarity and correctness. And to some extent, programmers have been spending the last 50 years or so doing the exact opposite, which then culminates in JavaScript. And in functional programming, we sort of try to take at least a few steps back and resurrect a little bit about the stability that we can get from the help of mathematics. And this is not strictly true what I'm saying, but it sort of gives a little bit of flavor of what this is about. There's a dividing line. We have math on one side, and we have not math on this side. And as long as we can stay on the mathematics side, which we can't really when we are programming, because we're going to need to read the disk, and we're going to need to do I/O, and we're going to need to print on the screen, and all of these things, immensely important things. But what we should really strive for is keeping as much of our code as possible on the mathematical side, if we want to have the help of mathematics in order to ensure that our program is correct, and also help us structure programs in a clever way. So on this side, all theorems apply of mathematics. On this side, if we're looking at it from a programmer's perspective, maybe. We don't really know. Because if you look at normal programming, it's sort of mathematical-ish. There's logic, there's a sort of a lot of mathematical things going on in programming, but it's not quite. And that's actually the sort of at the heart of this little dilemma and problem. So we don't really know. Maybe it applies. Strict logic. Here, well, sort of maybe. Maybe. We don't really know. Because suddenly if you change global memory and override some memory location, you might end up in a situation where x equals x actually as a logic statement fails, because x got changed in between evaluating one side of the Boolean operator and the other one, because some other thread did something which changed the memory. It's not to say that that can't happen in practice in functional programming. There might be cosmic radiation and who knows what, but this is really from a slightly more serious point of view. Here, like logic works, that means that x does not equal x plus 1 ever. It cannot happen. Whereas on this side, x equals x plus 1 is considered a statement of truth by the compiler. This is actually a statement of truth and has a semantic meaning which is breaking logic. This is not on functional programming side. This can never, ever be true. You can't update variables in functional programming. We don't have mutable state. Yes?
Can we also mention one of these math theorems which applies in functional programming and which we maybe like to have in programming, which is not guaranteed in languages that do not follow this strictly? Just to have one example for a theorem, and like one that I have in mind, maybe composability.
Yes, and that's composability is really also a key and feature of doing functional programming, which is hard to do in where you have mutable state. And composability will allow us to build complexity by having functions, taking functions as argument, for example, and building complexity that way. And it's a very convenient technique. It's also at the heart of something called category theory, which we will not be discussing a lot. We will mention it a couple of times, which is really a mathematical theory of composition. So we will get all this wonderful help from the mathematicians without having to bother with mathematics ourselves, but we will get all these nice guarantees from the mathematicians that what we are doing is actually safe and sound compared to ad hoc and Hail Mary. And at the same time, what we will get is since we are using, pick up stuff from mathematics and things that they have figured out and things that work and will compose and will fit together and guaranteed to be right, we will actually have this guiding light of how to structure our programs. We have this framework of thinking and doing things that will help us in our quest to make just simple software, really, which is great. On this side, we sort of end up not really having it. So, no mutable state here. And here we have mutable state. And this is really one of the key properties of functional programming. And more or less, you can say that the moment you get rid of mutable state, you necessarily end up with functional programming, more or less, in some form. And this makes also with some techniques that we're using in normal imperative programming, we can't use in functional programming. For example, for loops. We can't have them in functional programming because a for loop has a loop counter which gets incremented and incremented and incremented. And we can't, and that gets changed. That's a mutable thing, and we can't have that in functional programming. Mathematics doesn't have a concept of mutable state in this context. Which means what mathematicians do when they want to loop is they recurse. And we will see how we can do this in a way that is equivalent to just normal looping from a runtime perspective. Another cool thing that we will do is that we will actually almost never recurse, because we will abstract away recursion into nice little ways of looking at the world, which allows us to recurse without thinking about it. Because recursion is hard, really hard. So I think that was more or less all I had. One of the things I want to say as a final little remark for this session is that you will likely find that functional programming is a little bit strange when you first encounter it, because you have to think about problems differently. And you have to look at the world slightly differently, and it will feel awkward in the beginning. But I can promise you, once you get going and once you get your brain sort of tuned into it, it just becomes normal programming. It's just plain, simple, ordinary bread and meat and potatoes, brown sauce programming. Just like anything else. But without a lot of bugs, often. So that's basically all for now. Until next time.